Hi, everyone. This is Weina. So it's my great honor to be here to share our recent study on the achieving low carbon concrete with high mechanical properties using calcium carbonate suspension produced by CO2 sequestration. So for now, I believe many of you have a strong feeling that the global warming is getting worse, right? Just a few days ago in our area, the New York area, the temperature reached up to 26 Celsius degree, so which is really abnormal. But unfortunately, as you can see this figure, the carbon emission is still climbing. So the cement production, this thing for related to us, is CO2 extensive, and is for now is identified as a major source of global CO2 emission. So as a researcher in this area, we have mainly two ways or two pathways to reduce the CO2 emissions. The first, generally, people are using some of the waste materials to replace the cement to reduce the use of cement in concrete, such as the supplementary cementitious materials like the slag, the fly ash, and also the fillers, such as the limestone powders, and also the recycled concrete aggregate powders. And the second pathways, for now, people are trying to reduce the CO2 emission by sequestering it into concrete through like different stages of concrete manufacturing. So the first stage, we call it pre-treatment stage. So in this stage, the raw materials, especially the solid wastes, such as the steel slag, the recycled concrete aggregate, are cured in a reactor with a very high concentration of CO2. So the idea behind is that the wastes are normally used for this purpose has a high content of calcium oxide or magnesium oxide that can react with the CO2 and moisturize the condition and form the calcium carbonates. And with time, the calcium carbonate will form a shell on the top of the surface of the wastes, and so that you can use it for upcycling back into the concrete. And the second is during the mixing stage. So what have been done is that the liquid CO2 is injected into the fresh concrete during concrete mixing. So what happened in the mixer is that the CO2, the injected CO2, reacted with cement and water and formed the nano-sized calcium carbonate particles. And that will significantly increase or improve the mechanical properties of the concrete inside. And the third stage, we call it curing stage. So this one have been intensively investigated. So the concrete is cured in an environmental chamber, something like this, with very high concentration of CO2 and with controlled pressure, temperature, and moisture. So instead of promoting the cement hydration just as the conventional water curing, the CO2 curing or the carbonation curing is to promote the precipitation of calcium carbonates and to refine the pores of the concrete specimens and densify the microstructure. With that, the properties, especially the mechanical properties and durability of the specimens will be enhanced. So this is the main pathway or the main methods for the sequestration, CO2 sequestration. But for the curing methods, there's also some limitations. No method is perfect. So the first one, the pre-treatment one, as you can see, it requires a special reactor to allow the injection of water, the CO2. And also it might require something like the rotator to homogenize the raw materials and make it fully exposed to the environment or to the CO2 and water so that it can be carbonated fully. So for this kind of method, it is good for high CO2 sequestration rates, but it is hard to be implemented for large-scale concrete production. So for the second one, if you remember, this method injecting the CO2 to the concrete mixer during the mixing. So this method, the limitation was reported as the CO2 sequestration rate is pretty low. And this can be due to several reasons. One is that the CO2 has very low dissolvability into the water. And second, the CO2 have very, very low reaction rate with the alkalis in the fresh concrete. And also, as the kind of mixer is hard to be really enclosed or sealed, so the CO2 is highly possible to release back to the atmosphere. So for the last one, the last method I just introduced is the CO2 curing. So this method also, the CO2 sequestration rate is reported low or limited because the concrete core, as you can see, is hard to be carbonated because for the precast elements, you normally use a formwork. And also the outer layers will be densified with the carbonation, and that will prevent the CO2 diffused into the core side of the specimens. So this is, and also for this kind of curing, it is hard to be applied to cast in place concrete application. So it's normally used for precast application. So by review all of the study, so what we want to do is to enable the cast in place concrete application with good CO2 sequestration rate. So what we do is we bubble the CO2 into the calcium-rich solution to prepare the uniformly distributed calcium carbonate suspension. And then we add this suspension to the mixing water. Okay, so, and then we use this to prepare the concrete, just to pour it into the dry ingredients and prepare the concrete specimens. So as you can see, this whole process is compatible with the existing industrial facilities, and it is convenient for large-scale production. So in this study, we prepared two groups of calcium carbonate suspension. And the first one, we call it CI suspension because it is prepared by the injection of CO2 into different concentration of calcium hydroxide and with a controlled speed. By this way, we form the calcium carbonate suspension. And again, we call it CI suspension. And as you can see in this figure, the important is that we should use an air stone to distribute the CO2 to form a better distributed calcium carbonate particles. And we also prepared to compare the performance of the CI suspension. We prepared a CP suspension. So this one is prepared with the commercially available nano calcium carbonate powders. Basically, this can be purchased on the markets. And here, this table shows the physical and chemical properties of the nano calcium carbonate powders. And one thing I want to note is that the particle size of this type of nano materials is in between 30 to 60 nanometer. So as just like many other types of nanomaterials, when we use the nano calcium carbonate powders to prepare concrete, to disperse it or to uniformly disperse it is the key, is very critical, because the nanomaterials are prone to agglomerate. So if it is agglomerates, it will be hard to really perform well in the concrete matrix and give a very well mechanical properties and durability. So we should disperse it. So what we did for this study is we just use ultrasonic water bath at 20K hertz for 10 minutes. before we use this suspension to prepare the concrete. So as you see, this process for dispersion of nanomaterials is also hard to be utilized in large-scale concrete production. So in total, we have investigated 10 mixtures with different concentration of calcium carbonate suspension. And again, this suspension prepared by both CI, the CO2 injection methods, and the nano calcium carbonate powders, the CP, okay, from 0 to 6%. And this calcium carbonate is used to replace the cement. It's not an addition, it's a replacement. Okay, so in terms of the key properties, just look at the mini slump spread, which represents the flowability. As you can see, as long as we increase the calcium carbonate suspension concentration, the flowability will decrease. And the CI methods obviously have a pronounced effect on reducing the flowability. And in terms of the compressive strength, as you can see, both the CI methods and the CP methods increase the compressive strength first and then decrease. And compare with the control, the 28 days compressive strength of the CI mixtures at the optimum dosage, which is 2%, increased by 16%. And the CP methods, or the CP mixtures, at its optimum dosage, which is 4%, showed 8% increase. So overall, the CI mixtures shows better performance than the CP method. So we're trying to figure out the mechanisms. So the first we evaluated the hydration and phase development. So as you can see, both the CI and CP methods promote the cement hydration reaction. So compared with the control, the time to reach the peak was accelerated. And also, like, the more hydration product was generated by use of the calcium carbonate suspension. And also, if you compare the CI mixtures and CP mixtures at the same concentration, the CI mixtures shows the shorter time to reach the peak, and also it shows high amounts of hydration product. So it also measured the porosity. So in general, the capillary pores in between the 10 to 1,000 nanometers were significantly reduced by use of the calcium carbonate suspension for both the CI and CP. And it shifted to the pores with the finer size for both the mixtures. So the reason, is basically by two effects. One is a filler effect. The calcium carbonate is an inert kind of nanoparticles. So it can, with the higher particle packing densities, it can help to fill the pores with those like different sizes of the particles. And also it has seeding effect as it has some nanoparticles inside. So nanoparticles can be worked as a nucleation sites and to promote the precipitation of the hydration products or promotes the cement hydration to fill the pores. So this is why when we use the CI and CP methods, we can see the reduction of the pores. And again, compare with the CP mixtures, the CI mixtures at the same concentration of calcium carbonate has lower porosity. So we're trying to figure out why the CI mixtures have better performance. So this is what we have done. We measured the particle size distribution of the calcium carbonate in suspension. So as you can see, the CI mixtures shows a finer particle size, a better dispersion and homogeneity than those produced by CP methods with the ultrasonic dispersion. And if for this one, this solid black line, so this one is actually, we didn't do any treatment. As you see, the particle is really, really bad distributed. But unfortunately, if we just do this measurement right after we produce these particles, it gives us a very good dispersion. But if we wait for, just make the suspension stay still and wait for 10 minutes to up to 30 minutes, you will see that the particles move to the right side. So which means the calcium carbonate particles tend to agglomerate with the retention time. So we don't want that happen. So for now, because of that, for now, we're trying to use some kind of cost-effective technology to stabilize the calcium carbonate particles in the suspension for a longer period of time. So here I just show you some of our preliminary studies. So we use polymers, works very well actually. So this I showed you the polyacrylic acid. So we use that to establish the particles, and we found a very good results. And you can keep the uniformly dispersion level at least 24 hours. And for now, we are trying to, like I said, just develop the more cost-effective methodologies to stabilize this kind of particles for like future larger scale production of concrete. So what I just showed you, the dispersion is in a suspension, and now I showed you the SEM observation of the calcium carbonate particles in a concrete matrix. So as you can see, again, the CI mixtures at 2%, it also shows a better calcium carbonate or particle distribution than the mixtures or the concrete prepared with the CP methods at the same dosage. So as you can see, we observed a lot of agglomerations for the CP mixtures. And to confirm the dispersion level of the different mixtures, we also use the specimens. We tested for the composite strengths, and we divided into 16 pieces. And we measured the calcium carbonate content using the TGA. And as you can see in here, the CI mixtures at 4% also shows much more or less dispersive than the CP 4% mixtures. So this means the CI method indeed has a better calcium carbonate particle dispersion level than the CP method. And finally, we also evaluated life cycle carbon footprint, and because maybe some of you may ask, you use the calcium hydroxide, so that is CO2 intensive as well. So how about life cycle carbon footprint? So this is it. So what we did is we calculate the strength normalized carbon emission, and the C represents that. And the CE here represents the unit carbon emission of an ingredient. And the CS represents the unit carbon sequestration of an ingredient. M is the mass of an ingredient. And the FCU represents the 28 days compressive strength. So here it shows, this table shows the carbon emission and carbon sequestration of the raw materials we used. As you can see, the calcium hydroxide and nano calcium carbonate powders, they are high carbon emission, right? But compared to the cement, it's significantly reduced. But compared with the nano calcium carbonate powders, the calcium hydroxide has higher carbon emission, but at the same time, it has very good CO2 sequestration values. So that's we can say that the total carbon emissions for these materials is low. It's much lower than just simply use the nano powders. So what you can see here is for the CI mixtures with the optimum dosage of 2%, we observed a 15% reduced for the strength normalized carbon emission. So I would say the CI mixtures is better than the CP mixtures at the optimum dosage. Oh, sorry, at the same dosages. So in conclusion, this research proposed an alternative approach to utilize the CO2 to prepare low carbon cementitious materials with relatively high CO2 sequestration efficiency and reaction rates. And also it can produce a uniformly distributed or dispersed nano-calcium carbonate particles with relatively low energy consumption. And also it gives us high mechanical strength or improved mechanical properties. And importantly, it is available for both the cast in place and precast concrete applications. And this research was funded by National Science Foundation and the New Jersey Department of Transportation. And here is a contributor, so Mr. Zhuo and Mr. Du. So those are the first PhD students of mine, and they are really working hard, and they are approaching to graduate next semester. And Mr. Liu is an expert in low carbon concrete, and Mr. Du is expert in UHPC. With that, I would like to thank all of you for your attention and would like to take any questions if you have. Thank you. Hello.
Thank you, Dr. Meng.
Okay.
Very impressive presentation. So
thank you.
Does anybody have any questions?
Yes, if you can type in the chat, or if you have maybe something in mind, you can also email me and I will respond to you. Thank you.
Okay. Okay, it looks like okay. Or just feel free to ask Dr. Meng.
Yeah, I will stay for a couple minutes. If you have any questions, please just use chat, or maybe I can respond to you. Thank you.
Okay. I'll probably wait another 1 minute for questions.
Okay.
If you don't want to ask now, just feel free to email Dr. Meng, because she has already shared her email address on the screen.
Sure.
Okay, I think I'm gonna move on to the next speaker.
Sure.
So, oh, we got one
stop sharing.
from Dr. Zhong. Great talk. Have you tried to sonicate the CI chloride prepared calcium carbonate and check its effects on the strength of the prepared concrete?
Oh, thank you, Dr. Zhong, for your question. That's a good question. Unfortunately, we didn't do that because, as I mentioned, for this method, we're trying to use it for large-scale concrete production as driven by a project. So we're trying to simplify the whole process as much as we can. So if we have used the sonification, so it will make the process difficult for the large scale production. So we didn't do that. But as scientific work, I'm sure the result will be interesting. So maybe I will do something and see what the effect looks like. So if you are interested as well, I will definitely share the results with you. Thank you.
Thank you, Dr. Mo.